Hello and welcome to day 3 of kinetics. Today we're going to be talking about deriving rate laws from steps in a mechanism. And to start, I think we're going to simplify things a little bit to talk about a reaction that happens in a single step. So because the reaction happens in a single step, this means that let's change that back to black, that the overall balanced equation is equal to the mechanism. Okay, you got to be a little careful about how things are talked about in this section. A reaction that happens in a single step means that the overall is equal to the mechanism. But everything that I'm talking about today is really holds true for single steps in a mechanism. Okay? All right, so my question to you, and I want you to pause and think about this. What determines how fast this reaction will happen? Okay? There are kind of two things that I'm looking for here. So what determines how fast this reaction will happen? So hopefully you came up with something along the lines of how often A and B collide and whether the collisions are productive. Okay, so how do we affect these? How do we affect, well, let's start here, whether the collisions are productive or not. How can we increase the number of productive collisions? Hopefully what pops into mind right away is temperature. Okay, if we give more energy, there should be more productive collisions. Okay, now how often A and B collide? Well, we could increase the numbers of A and B, which, if we're saying increase the number in a given area, this would be increased concentration. So the rate of this step should depend on concentrations of A and B. And for example, the rate should increase directly with the concentration of A. If you need to see, you should be able to logic this out. Kind of go back to the image of how concentration affects rate and kind of convince yourself that rate should be directly proportional to the concentration of each of these. If you need me to go over this with you in class, we'll have time at the beginning of class, so just let me know. So I can come up with a rate law, it turns out, that rate is equal to K times the concentration of A times the concentration of B, because the rate, should be directly proportional to the concentration of each of these. If I raise the rate of A, if I raise the concentration of A, the rate should increase. Okay? Well, my next question then is, how about the reaction of A plus 2B goes to C? Oh, well, that's a little different. Well, maybe not. Notice that this can also be written as A plus B goes to C. Now if I do that, now it should be a little bit more clear what I'm looking for here. Okay? Rate equals K times the concentration of A times the concentration of B times the concentration of B. And if I do this, then this just becomes rate times the concentration of B squared. Okay, so what I'm getting from this is that the powers on these, so the order of the reaction, depends on the coefficients. Of a mechanism. This is for a mechanism only. Notice last class we talked about how the order does not depend on coefficients for an overall reaction, only for a mechanism. This is really, really crucial. You got to keep this in mind. Okay, so what happens if we have a reaction that doesn't happen in one step? Okay. Well, now we want to talk about something called the rate determining step. And to use this, I am going to have just this world-class diagram here. Here's me with my sunglasses on, because, you know, I always have my sunglasses on. And I need to get all the sand from bucket A to bucket C. And I'm going to do this by taking a small cup and then pouring it into C. Now I want to be careful. I don't want to spill, so I'm going to pour through this funnel. Unfortunately, this funnel is really small. Really small funnel. Okay, so got a couple questions here. What is my overall reaction? Okay, I want you to pause and see if you can come up with the overall reaction. The overall reaction is A goes to C. All right, I need to get the sand from bucket A to C. Now if I ask for the mechanism, pause it, think about it, see if you can come up. All right, the mechanism that I'm going for here is A goes to B. So sand goes from bucket A to my cup, B, and then B to C, where I dump B into C. Now, A goes to B, this is very fast. Okay? And B goes to C, this is actually really slow because I have to wait for the sand to go through the funnel. So what determines how fast I can do this overall reaction A to C? Well, it's going to be how fast the sand goes through this funnel, right? So we call the slow step in the mechanism the rate determining step, which we sometimes abbreviate RDS. Okay, so the rate determining step determines how fast your overall reaction goes. And we can apply what we came up with on this page to the rate determining step. So let's look at an example. All right, so I have this overall equation and I have a mechanism, okay? And I have a slow step and I have a fast step. Now the slow step is the rate determining step, RDS, because it's slow. It's slower than the fast one, all right? So if I wanted to come up with a rate law based on just this mechanism, okay, it would be rate equals K times the concentration of NO2 to the first power, because the coefficient in front of NO2 is 1, times the concentration of F2 to the 1, because F2 also has a coefficient of 1. Okay, so the rate law for the overall reaction is really just the rate law of this slow step. And that's really all we're doing today. Okay, that's all we're adding on.